Hi, my name's Patrick, and I just want to say, Tiger's back, baby.
And I'm Graham, and I'm from Canada,
And this is our presentation on the differential equations application of bungee jumping. Now, whether or not you're an avid bungee jumper or a professional bungee jumper, you do need to take into account the fact that there are mathematical equations regarding bungee jumping. Now, the purpose of this presentation is to model the motion of bungee jumping using differential equations. Now, this model that we're going to describe is useful to many people. This is useful to the owners of the bungee jumping company and hopefully to you, because if you don't listen to our bungee jumping tips and tricks, it might not end so well for you.
Now, in the first portion of the bungee jump, there is a principle at play, and that's Newton's second law. And now, it's not so much when you're falling, that's more Newton's third law, which is for every action, there's an equal and opposite reaction, but we'll get to that with the wind resistance. Now, Newton's second law is important because at the end of the free fall, you will have a different force than just your weight times gravity. And that is important to know at the beginning when setting up our spring equation. Another principle, which is perhaps the most important thing for avid bungee jumpers and people interested in the topic, is Hooke's law. And that has to do with the proportionality between the force needed to stretch a spring and the distance that the spring is stretched. And the proportionality constant is known as spring constant, or K. So, just for everybody who wants to know, the higher the K value, the harder it is to stretch the spring, or the bungee cord. So for anybody trying to get a bungee cord, don't get one that's with the K value too high and somebody that's too light, because then they could just be jumping like they're on a rope, and that would not be good.
Now, as we mentioned, there's a spring system that works within the bungee cord itself. Now, we can show that the bungee cord acts as if it is a spring. This can be considered in an inverted spring mass system with a dampening constant. Now, this is an inverted mass spring system due to the fact that there is a mass attached to the bottom of a spring suspended vertically. Now, this is the bungee cord jumping off of a high cliff within this situation. Now, the differential equation seen there is that mass multiplied by the second derivative of y respect to time, plus the lambda, which is the dampening constant, as Patrick so kindly mentioned, multiplied by the derivative of y with respect to time, plus the spring constant, which is k, multiplied by y. Now, this is all set to 0 within this situation.
Now, as I mentioned earlier, during free fall, there is also the force of wind resistance. And that is the negative reactant force acting upon the jumper as he falls through the air. Because in our situation, we're not jumping in a vacuum because we wouldn't be alive in a vacuum. So, in order to even out the forces, we introduced a proportionality constant of mass times gravity over velocity squared, and we factor that into our equation for free fall. Another principle at play here is damping. Similar and just as important as knowing the spring constant for you avid bungee jumpers is the damping constant. You need to know all about damping, because if the damping constant is too high, it's like jumping on a rope. All you really need to know is there are 3 cases of damping. There's the underdamped spring, the overdamped spring, and the critically damped spring. Now, the underdamped spring, which is what we're going to be exhibiting in this case, allows long undulations of the spring and soft returns to equilibrium. The overdamped spring and the critically damped spring are pretty similar, as they both don't allow for any oscillations of the spring. It's just the overdamped spring returns to equilibrium in a shorter amount of time, or a longer amount of time, than the critically damped spring.
Now there are some assumptions that we need to make within these calculations that we're going to describe later. Now, we're going to assume that the mass of your body will be at your feet. Now, this will be easier within the calculations, as the center of mass will act as the point of which all the mass is stored. This will be at the bottom of your feet because it makes calculations easier due to it will be the length of the bungee cord within the situation. Now, when your body is above equilibrium position of the cord will bend, but we will assume that there will be no force on your body. Now, this will just be easier to simplify the calculations. Within the system, the force of gravity will be acting relentlessly on your body, and there will be an air resistance that was mentioned earlier that will also be acting. Now, there is a mathematical model that we are going to describe. There are two parts within this mathematical model. The jump can essentially be broken up into these two separate parts. Now, the first part is the free fall. The free fall is essentially when only the mass of the person is falling due to the force of gravity and the air resistance within. The sum of the forces is equal to ma within this situation. Now, ma is equal to the force due to gravity plus the wind resistance within this. So ma is equal to mg plus f sub w.
Now, the second part of our model is the spring motion. And that is compiled of mass times acceleration, Hooke's law, and the damping constant, which can be seen here in our equation of mass times y double prime, or acceleration, plus lambda y prime, or velocity, and ky, which is the spring constant and position.
Now, we can create a derivation from the equation that we had earlier. Now, we would do this in respect to the underdamped case, due to the fact that, as we mentioned before, the underdamped case is the case that we would like to use during bungee jumping motion. Now, we start off with y double prime plus lambda over m y prime plus w sub 0 squared y is equal to 0. Now, we're going to divide m throughout this equation so that we can separate the y double prime. Now, k over m will be equal to w sub 0 squared within this situation. Now, in order to solve this equation, we must assume a particular solution, y is equal to e to the xt. Now, this is an easy general solution that we can use within differential equations. Now, substituting in, this leads to an auxiliary equation, as seen there, where e to the xt, and then in brackets, x squared plus lambda over mx plus w sub 0 squared is all equal to 0. Now, solving for the roots within this situation gives us two roots, x1 and x2. These will be the negative lambda over 2m plus or minus the square root of lambda squared over 4m squared minus w sub 0 squared. We can write a general solution from this, and this is seen below with the constants a and b within this situation that we can solve for later on if we have solutions within this. Now, there are three general classes of interest due to the fact that m, lambda, and w sub 0 are all positive. We can see here that if w sub 0 squared is greater than k squared over 4m squared, the underdamped case will occur. Now, this is auxiliary motion, oscillatory motion that we would like to occur during our bungee jumping. But, however, if w sub 0 squared is equal to the k squared over 4m squared, we will have a critically damped case, and if w sub 0 squared is less than this k squared over 4m squared, an overdamped case will occur. Now, for the underdamped case, which is the case we'd like to use, it will give us the form. We will solve for w1 squared is equal to w sub 0 squared minus lambda squared over 2m squared. This can be used and substituted in the equation we had in the earlier slide at the bottom there, which was our general solution. Now, the quantity within the parentheses can be used, the Euler's formula, which may be used to put into the form c times cosine of w1t plus a constant d. Therefore, the equation that we can use to solve a bungee jumping case within the underdamped case will be y is equal to c, which is the constant, multiplied by e to the negative lambda over 2m, all multiplied by t, multiplied by cosine w1t. Now, here's an example of the graph of the underdamped case. We see on the left-hand side here that this is the distance that the spring will travel with respect to time. Now, at the very beginning of this motion, there is a great distance that the spring will travel. This will be at the very beginning when the mass of the person will effectively combine with the force due to gravity will force the spring to stretch to its max distance. Now, this will over time become less and less of a distance that it will oscillate at, and will occur in a bungee jumping fashion like we would assume and want during our bungee jumping motion.
Now, I believe it's time for us to show you our example. Now, Ollie is having an early life crisis with exams just around the corner, and the ending of Game of Thrones not much further in the distance. So to take his mind off things, he decided to rewatch the entirety of Game of Thrones in anticipation for the final episode, and found that he was missing some action in his life. So the next day he decided to go to his local bungee jumping club to take a dive. Ali, who weighs 70 kilograms, stood atop a bridge attached to an underdamped bungee cord that is 50 meters long. The bungee cord he's hooked up to has a spring constant of 1,000 Newton meters and a damping constant of 3,741 over seconds. Find the general solution y of t. So in order to solve our differential equation, and set up even, we must first find the equivalent weight of Ali when he's reached the end of the unstretched length of the rope. In other words, we need to see how fast he's traveling when he reaches the 50-meter length of the rope. So first we go through some general physics equations. We calculate time to be 3.2 seconds. And then from that we get the velocity to be 31.3 meters per second. And with that we can calculate kinetic energy, or the force, at the end of the 50 meters. Now for Ali's 70 kilogram body, at the end of the 50 meters, he will exert a force of 34,420.7 newtons. Now, as I mentioned earlier, we factored in wind resistance. Now, it is mostly negligible due to the high numbers in our example, but we calculated it out to be 0.7 newtons acting in the negative direction. So the final total force that Ali is exerting at the end of the 50-meter unstretched length, or rather the beginning of the spring, is 34,420 newtons, which is an equivalent weight of 3,512 kilograms. With that, since we know our constants from the setup, we can set up our differential equation to be 3,512 times y double prime plus 3,740 y prime, which is the damping constant, plus 1000 y prime, which is the spring constant. And since we know all of these values now, and we know the derivation for the underdamped harmonic oscillator, we can just plug the numbers on in, and after doing so, and our general solution can be seen here as C times E raised to the negative 6,567,440 t times cosine of negative 12,987,600 t. Now, that was our general solution and our general position found, and we hoped you learned a lot from this presentation. Now, there are a few things that I would like Graham to remind you of.
Next time you go bungee jumping, make sure that you're experiencing the underdamped oscillatory motion. Now, this will make sure that you don't break something, hurt something, or harm something within your bungee jumping experience. And also, make sure that your dampening constant is not too high and it's not too little, because when it's just right, it's just right. Now, I just want you guys to have a great day,